To the further advanced topics of the statistics module, we will see what is skewness and kurtosis and the different statistical models which are used to describe the data or which are basically used as models of the data so that the further inference is possible. These different models, we call them as statistical distributions. Some of you might be familiar with these names: normal, binomial, Poisson, negative binomial, exponential, gamma. These are some statistical distributions used as models. Then examples where these data distributions could be used. So let us begin with the concept of skewness. See, when we started with the data exploration, which is nothing but the understanding of the data, we started with, first of all, as the measure of central tendency, which gives us a representative figure for the entire data. Then we realized that only measure of central tendency is not enough. We should know something about the spread in the data. So then we talked about and studied dispersion and measures of dispersion. Now there is a third angle to looking at the data. Now with measure of central tendency, you know the point around which the data has been clustered. The measure of dispersion gives you the extent of spread in the data, but now you are interested in knowing whether the observations are symmetric around a measure of central tendency. I mean, if there are same number of observations which are the concentrations of the observations on both the sides of the mode, the most general observation is same as it is the situation in the normal curve. So this curve, you see that if you cut this curve into the middle, then the one part of it is the mirror image of the other part. So that is called as a symmetric curve. And this symmetric bell-shaped curve is known as the normal curve or normal distribution. Not necessary that every symmetric curve has to be a normal distribution, but a normal curve is definitely symmetric. When we were seeing the histograms, I had shown you that the bars are becoming taller and taller, and then after some point onwards, they start becoming shorter and shorter with the same amount of reduction in their heights. So if that is the situation, then that data is symmetric or the distribution is symmetric. On the other hand, this is a scenario where you come up with the positively skewed data. That means the higher mass is concentrated on the lower values of the x-axis. See, on x-axis you always have the response variable or the variable of interest, and the y-axis has frequency. So more frequencies or more observations on the lower side and less observations on the later part of the x-axis means very few high observations but very large low observations. That is the situation whenever you come across the positively skewed data. This kind of data we had observed whenever we had seen that myeloma data and we were looking at the survivals of the patients. This is the third type, that is negatively skewed distribution or negatively skewed data. Here smaller observations are less in number and higher observations are more in number. So it is exactly the reverse of this positively skewed data. Now what happens with the measures of central tendency for the different types of skewness? In case of symmetric distribution, the skewness is 0. That is mean, median and mode, all of them coincide here. Is that obvious from this picture? To certain extent, yes. Mode of the distribution is the peak value and the peak value is at the center, so it is the median, And mean, as I mentioned, that it can be thought of as a measure of central gravity. So if you can balance this curve on this point, that will give me the value of mean. So mean, median and mode are all of them same. So for any symmetric distribution, it happens, and then the measure of skewness is equal to 0. There are several measures of skewness. We will not go into the details of them. We are just trying to understand these different concepts. I would like to specify that throughout this session, our goal is not to understand in detail or not to learn any formula for any of the topics discussed in this session, but to understand the concepts behind them. So in case of positively skewed distribution, what happens here? That the peak comes earlier, so the mode comes first. Median is always between the two because it has to cut the observations into 50% on both the sides. So mode is on the left hand side, then comes the median, and then comes the arithmetic mean somewhere over here. Exactly the reverse thing happens for negatively skewed distribution. Mode is here, the maximum value, and then here somewhere is the median, and here somewhere is the arithmetic mean. So with these three, then statisticians compute lot of things. You can take the difference between mean and mode, and that gives you the value of something which you can call as the, and divide by sigma, the standard deviation, which is one measure of skewness. So several measures of skewness can be defined, because all the time you are not going to draw the curves and then see, and even if you see, you should know what is the amount of skewness in the data. So in order to get a proper measure, one has to know some measures of skewness. Similarly, there is one more angle to look at the distribution in the data. After skewness, which talks about the symmetry, actually it is the lack of symmetry. Skewness is lack of symmetry. One can think of looking at it as the kurtosis. So kurtosis is essentially the peakedness in the distribution. It is not the peakedness in the values of the data, but it is the way in which if you draw the histogram and draw a smooth curve around that histogram, around the tops of each of these bars, then you get this as a frequency curve. So suppose these are the frequency curves, and there are three frequency curves displayed here. The middle one is corresponding to the normal distribution, and that is known as mesokurtic. So considering normal distribution as the standard, one can classify the other distributions into the other categories. For example, this one. What is the peculiarity of this curve? That here it is symmetric, but it is flat. So it is flat, and therefore there is a very less kurtosis. So if you compute the measure of kurtosis, it comes out to be negative, and that is called as platykurtic. This is called as leptokurtic whenever you get a higher peakedness as compared to the normal distribution. So with respect to this as a standard, either it is flat or it is more peaked, you are going to call it as platykurtic or leptokurtic. And then again there are several measures of kurtosis available in the data. This is what I have said while describing it with the help of that figure. So distribution having peakedness equal to normal distribution are called mesokurtic distributions. Distributions having peakedness having more peak than that of normal is called as leptokurtic, and having peakedness having less peak than that of normal is called platykurtic distribution. Now why all of them, and why one should be interested in the kurtosis, and why one should be interested in skewness, and why one is always comparing with the normal distribution? We will try to answer these questions in a short while. People were not satisfied with merely the data exploration. Okay, if you have huge amount of data, you can plot several graphs and compute several measures of central tendencies and dispersion and skewness and kurtosis. But what next? What next means, suppose you have to answer some questions on the behavior of that particular variable under consideration. For example, that survival in that myeloma study, we were talking about the survival in months of a patient in that clinical trial. Now suppose I am interested in knowing what would be the average survival of a myeloma patient. How to answer that question? One way of answering that question is you have that data. But remember that data is a sample, that is not the population. You can compute that sample mean and that gave us the average survival in that particular data. But in general, if you want to report it as a conclusion or inference of your study, what are you going to say? That if that 13 months was the mean, then on an average, the 13th month is the average survival of a myeloma patient. If you say that, will anybody buy that statement? So that's a question that we would like to answer. So only exploratory data analysis is not going to lead us to any conclusion or inferences. We have to go one step beyond that. And going one step beyond that is the use of statistical inference. So statistical inference was developed by great statisticians such as Fisher, Neyman, Lehman. One can mention other names also, but these are the three important statisticians who have developed this branch of statistical inference. Now what is done in statistical inference is that after doing the exploratory data analysis, you get some hang of the nature of the data, you get some idea about the patterns in the data, the behavior in that particular variable, and the important thing is that you will model that data. You will model that data statistically. Means you will assume that that particular endpoint is following some distribution, statistical distribution, and once you get that statistical distribution as the model for that data, then the life of a statistician becomes very easy. In a very crude manner, I would like to explain to you what does statistical analysis inference do. See, for example, if there is a tree and you want to estimate the amount of wood present in that tree. Okay. Now, unless you cut that tree and measure it, it's not possible to get the idea of that. What one can think of is that consider that tree as a cone. I mean, you can model it as a cone. Everybody knows cone. Okay. And then you can measure the height of the tree by some methods. Okay. So if you measure the height of the tree and you have the girth, then you can estimate the volume of that cone, which is a model. See, remember, you are estimating, you are not measuring. There is a difference between actually measuring and estimating. So you can estimate the volume of that cone which you are using as a model for that tree. And then considering the density and blah blah blah, you can come up with the estimate of the wood, amount of wood available present in the tree. Similarly, your data might be having several fluctuations. Your histogram may not be very nice. It is showing you some fluctuations. But if you think that my data can be modeled by, say, normal distribution, then I am choosing the normal distribution as a model for mimicking the behavior in the data. And once I get hold of that normal distribution as a model, then because all statisticians have studied that distribution and done algebra, employed calculus methods to compute everything, then I can compute basically the second point I am talking about now, that you can compute probabilities of certain events, assumptions regarding measures of central tendency, and dispersions can be made. For example, in that survival study, I will be able to find out what is the probability that a randomly chosen patient will survive beyond, say, 60 months? You will be able to answer such questions probabilistically, and that is the main advantage, and that is the purpose of understanding and learning statistical inference. So, these models are the building blocks for statistical inference. So, the models are important. So, now depending upon the various attributes of the data, we have seen some of them: symmetry, pickedness, variance, measure, etc. You can think of the model. So, choosing a proper model needs statistical expertise. It cannot be anyone else's job. You cannot just look at the data and think of a model that you will choose. Normal distribution is one such model which is used heavily in statistical inference. This is a continuous distribution. See, as we have classified the endpoints into different categories like continuous, binary, categorical, obviously the same way there are going to be different statistical models catering to these different classes. So, for continuous kind of variables, normal distribution is one such model. This is a bell-shaped curved model. It is also known as Gaussian curve because the statistician Gauss, who has invented this. Standard normal distribution is one particular member of that family of normal distributions with mean 0 and standard deviation. Graph of the normal distribution depends on the mean and standard deviation. When you talk about any statistical model or statistical distribution, that distribution is identified by some parameters. So, we call them as parameters. So, here in case of normal, mean, which is generally denoted by mu, and standard deviation by sigma. So, normal mu sigma is a family of normal distributions. So, if you specify mu and sigma, then the member from the family gets fixed. For example, if you specify your first name and your surname, then the person gets fixed. Then there is no ambiguity. If you just specify your first name, then who knows, there can be several people having the first name. So, these are called as parameters. So, when you specify them, the member from that particular group of distributions or the normal group, that particular distribution gets fixed. And then you can use that distribution for computing several probabilities, several questions you can answer, that what is the average survival, what would be the variation, and these questions you are going to answer. One thing always to be kept in our mind, that they are not the questions regarding the sample, we are answering the questions about the population on the basis of our sample, that is observed data. So, how does a normal distribution look? Normal distributions look like a symmetric bell-shaped curve as shown below. Now, you will say that this is also normal, that is also normal. What is the thing? Here, the mu and sigma, they are playing their roles. So, here the standard deviation is larger, here standard deviation is smaller. Example of normal distributions can be all different scores like IQ scores, heights of males or females, body temperatures, and most of the continuous variables. One can think of normal distribution as a model for them. And there is another advantage of considering normal distribution as a model. It will become clear in a few slides. Normal distribution, as I mentioned, that if you specify sigma, that is standard deviation, and mean, that is mu, the person gets fixed, member gets fixed. Here, this is a picture of having the same standard deviation, but same sigma, but different means. So, because of same sigma, you are getting the same as if you are drawing a freehand curve. Similar curves you are getting, but they are dislocated, so to say. So, their centers are different because their means are different, but the spreads are same. On the other hand, one can think of normal curves having the same mean. So the centers are same, you will see, but the spreads are different. So this is here actually your platy, meso and leptokurtic situation. All of them are symmetric. So this is standard deviation equal to 1, standard deviation equal to 5 and standard deviation equal to 10. So obviously the flatter one is having standard deviation equal to 10. Normal distribution is such a detailed topic that one can give a series of lectures on normal distribution. The famous Six Sigma limits also come from normal distribution. Here, these are two sigma limits. They are, if you consider this 0 as the mean, or in case of standard normal curve, 0 is the mean. If you go one standard deviation here and one standard deviation here, then it comprises of 68% of the observations. If you go further, 0.135, 0.135, so 13.5%, so in 27% will be added to this. So only 2.5% observations are below minus 2 sigma and 2.5% observations are above 2 sigma. And in case of 3 sigma, you will get still further lower number of observations. This would definitely sound you little complex, but the point here one wants to make is that, see, 2.5% gone here, 2.5% gone here. So how many gone? 5% in all. Okay. So if you don't want to worry about these 5% of the data, only concentrate from minus 2 sigma to plus 2 sigma and concentrate on that range and study that. So that is what is the point. So similarly 3 sigma limits, if you are considering 3 sigma limits which is going from minus 3 sigma to plus 3 sigma, it would be 99.73% of the observations fall within the 3 sigma limits or 3 sigma limits. So even though the range of the variable is from minus infinity to plus infinity, the mu minus 3 sigma to mu plus 3 sigma pocket 99.73% of the data. That is the peculiarity of the normal distribution. And generally, people have observed that for almost all observations, the situation is like that. The normal distribution was invented whenever they were studying the distances of the celestial objects from each other, and they were finding the errors. So the errors are generally normally distributed. Anyway, so we will not go into those things. I had mentioned that why normal distribution. There is one more point besides that it is occurring in the nature all the time. There is a famous central limit theorem in statistics which states that if the original variable follows any distribution, discrete or continuous, with mean mu and standard deviation sigma, then for large sample size, the sample mean x bar follows normal distribution with mean as the same mu and standard deviation as sigma upon root n, where n is the sample size you are looking. No matter what the shape of the distribution, if samples drawn from it are big enough, the sample means are normally distributed. So this is a famous central limit theorem. Advantage of this central limit theorem is that from any distribution you can come down to the normal distribution through the means and through the large samples. And the branch of statistical inference that deals with this kind of inference is called as asymptotic inference. Whenever it is affordable to take large samples and measure the observations on them, then you can go in for the means of the samples. then that mean also becomes a variable and you can talk about its distribution, and then you can take help of central limit theorem and say, what can you say? That my means of the samples are following normal distribution. And this, the astonishing fact is that your observations or the response variable could be discrete also. This happens even if you have a binomial random variable at the beginning, but the samples means become normal. You have a Poisson distribution in the beginning, but the sample means become normal. So that is the advantage of this theorem. So I thought of including it into this module, because everywhere now you are going to see that whichever statistical analysis you will be doing through SAS procedures, you will get the confidence intervals and they are based upon always the Z test statistic, which is the normal test statistic. So the computation of confidence intervals for population parameters, the asymptotic p-value computation. What is the notion of p-value? We will see in our subsequent lectures. P-value actually tells you what is right and what is wrong. It leads you to the conclusion whether to reject the null hypothesis. Basically, it leads you to the conclusion whether the treatment is effective or not. So the p-value is very important, and the p-value computation, if you are using large samples, what is large? Large is very small in statistics. It is only 30. So if your samples are beyond 30 or say around 30, you can very well consider the means to follow as normal distribution and employ the central limit theorem to come up with the asymptotic p-value, which leads you to the conclusion of whether the drug is effective or not. So that actually completes the story of the clinical trial study. Anyway, so similar as there is normal distribution, there are some other distributions in statistics which are used to model the data. You should be just knowing the names of these distributions and whenever they are used. Binomial distribution is a discrete distribution which is talking about the number of successes in a series of n trials. Now here, although it is written in the statistical language, it is talking about only a binary kind of experiment which results into either this or that. Newborn is either a boy or a girl, and we are interested in the number of girls born, so number of successes. So one thing is called as success, other thing is called as failure, and you are talking about the number of successes. Then you are modeling your data by the binomial distribution. Poisson distribution is used whenever you are counting something, counting the rare events. So the number of times that a rare event occurs during a particular time period or in a particular area. For example, the number of arrivals in a clinical study center in a day. There could be 0 arrivals, 1 arrival, 2 arrival, 3 arrival. So you are counting arrivals and then you can use the Poisson distribution. Another example could be the number of tumors generated in a specified time interval in an oncology study, the number of DNA fragments found from a sequencing experiment, the number of dead trees in a square mile of a forest. So whenever you are counting such events, you can use the Poisson distribution. Again, it is a kind of discrete distribution, not continuous. Binomial and Poisson both are discrete. There is another discrete distribution which is known as negative binomial distribution. And that negative binomial distribution, also known as Pascal distribution, is a random variable or is the number of x of repeated trials to produce r successes in a negative binomial experiment. Means what? See, if you are catching fish from a pond and then you are interested in catching say 10 fish of a particular species, you are going to stop only when you get 10 fish of a species X. So your trial is binary. You catch a fish, you see whether it is of the species X or not. If it is of species X, you will keep it aside. You catch the next fish and so on and so forth. So how many fish you will catch? You don't know. The minimum fish you can catch is 10 because you are going to stop only when you are going to catch 10 fish of species X. So minimum fish you are going to catch is 10, but it can be 1000 also. By 10,000 or by 1000 catches also you may not get 10 fish of that species X. So if you are interested in that kind of situation, then you are into the negative binomial distribution. Suppose we flip a coin repeatedly and count the number of heads. If we continue flipping the coin until it has landed 2 times on heads, we are conducting a negative binomial experiment. And why it is negative binomial? Because means it is having similarity with binomial but sort of anti-binomial. Because here the number of successes is fixed here, that is 10 in case of that fish experiment. But in case of binomial distribution, the number of trials are fixed. You are going to flip the coin say 100 times and observe the number of heads. Understand the difference? In here, your number of trials are not fixed, number of successes are fixed. So it is a different way of looking at the situation and therefore it is called as negative binomial distribution. Anyway, there are some other continuous distributions now. This is one used as exponential distribution. This is always taking positive values, generally used as a life distribution. So this an example of an exponential distribution could be given as the lifetime of an electronic device. Now why electronic device? Because there is no aging. Exponential distribution doesn't have aging. So the probability of death at any point of time is constant. That is not true with living organisms. Probability of death increases with age. So here, so whenever this is the situation, you are talking about the exponential distribution. The exponential distribution is also used as the inter-arrival time of the arrivals in a clinical trial or at a telephone booth, duration of time of a car service, time until the next earthquake occurs. So basically, the exponential distribution and Poisson distribution, they go hand in hand whenever the occurrence of the events is according to Poisson and the inter-arrival times are according to exponential. This is too advanced thing to be known for you people, but anywhere if it comes across, you will be knowing that and then you will be happy that you know that beforehand. Similarly, there is a generalization of this exponential distribution to a gamma distribution. So this is a kind of generalized positive value taking distribution. This is having positively skew data. Some events that may be modeled by gamma distribution is amount of rainfall, size of loan defaults, manufacturing, load on web servers, the median weighted form of telephone exchange, etc. Although the examples are not here from the clinical trials domain, basically this is a positively skewed distribution and like exponential distribution, actually the sum of exponential independent random variables lead to the gamma distribution. Point here that I wanted to make is that there are several such distributions. One can think of Webel, log normal, extreme value distribution, and several other statistical models which are used depending upon the context of the random variables you are studying, and then appropriately the statistical inference follows. So in today's discussion, we started with the concept of skewness, then we discussed kurtosis, then how statistical distributions are used to model data, some statistical distributions which are commonly used, and the situations where they are used. Thank you so much for your patient hearing, and don't get bogged down by the theoretical details or the complexities of this particular